In the last video, we talked about simple exponential smoothing methods, but in this video, we're going to be focusing on the simple exponential smoothing statistical models. Now, last time we looked at the Algerian exports of goods and services and how changing the parameter values of the smoothing parameter can lead to different types of fitted series, which is highlighted here. Now, moving on to the advantages of using statistical models in forecasting, we know that in addition to generating point forecasts that methods give us, these models can also generate forecast distributions, which are very useful for model selection purposes. So you could have a wide range of models and you could pick the model that's best suited for a certain forecasting interval, forecasting problem, and things like that. Okay, the idea is to think about the uncertainty that is associated with a point forecast. Now, we had introduced some notation last time with ETS models, and for simple exponential smoothing, which is a model in which there is really no trend that you can see, or there is no underlying seasonal pattern, but the series sort of looks like it's all over the place. It is not displaying any trend or seasonality. You would only have a forecast equation that says that the forecast equals the level of the time series. Okay, and the level of the time series itself is a weighted average of the level in the previous period and the value of the time series at time t. Okay, now when we move to R, we are going to be looking at different applications, but the main function that we're going to be using is called ETS, corresponding to error, trend, and seasonal components. And these have a big range. So your error could be additive or multiplicative. You could have a trend, you could not have a trend, or you could have various other options similarly for the seasonal component. But when we're thinking about the simple exponential smoothing models, then we are interested in looking at a model which has an additive error, but no trend or no seasonal component. So that's why you have additive here, which represents the error component, and then nothing for trends and nothing for seasonals. So we did look at how we could rearrange terms and come up with an error correction form for this type of a model. Okay. Now, when we get to thinking about state space representations of statistical models, that has been really the innovation in the last 20 years in time series. These are usually represented by two types of equations. So the first equation here is a measurement equation, and the second equation here is a transition or a state equation. The measurement equation, which is the first one right here, is useful to establish a relationship between observations and states. Okay, so you have some observed values of a time series, but you also have some kind of states that are that could come from either levels, trends, or seasonal components. Okay, and these states are unobserved. So this is what we're trying to uncover using exponential models. So this is really, again, looking at the simple exponential smoothing models and what that would look like. So that would just entail the level term and nothing for seasonals and nothing for trends. Okay, now the model itself is subject to some sort of innovations or some source of error, but that is going to be the same error process each step of the way or throughout the time series. So epsilon t here is normally identically distributed with mean zero and variance sigma square. You have transition or state equations, which is the second equation here, which really governs the evolution of the unobserved states through time. So this could again be the states are unobserved. This could be level, trend, or seasonal components, but again, in the context of simple exponential smoothing models, this is not going to involve trend or seasonal components. Now, you could also have models where the errors appear in a multiplicative form and not in an additive form. You don't have to worry so much about this at this point, but really in terms of notation, your epsilon t is going to be a little bit different than the epsilon t that you had in the additive model. This is just going to be, in this case, in the multiplicative format, this is going to be the error, the forecast error, normalized by the fitted value at time t. Okay, so you have the forecast error in the numerator, and then you have in the denominator you have your fitted value. So again, the assumption is the same, that this is normally identically distributed with mean zero and variance sigma square. Now, if you want to substitute the fitted value and you want to equate it to the level at time t minus 1, you can kind of write it in the error correction form as before. Okay, so, to simplify things, again, in the multiplicative form, you would have a measurement equation, which is saying that yt, right, this is your observed value of the time series, and the measurement equation is connecting or governing how the observed value of the time series relates to the unobserved components. Here you have a multiplicative format where yt, which is your observed value of the time series, equals lt minus 1, the level itself, plus lt minus 1 times epsilon t. So your error term is multiplied with the level at t minus 1. And finally, your state equation is going to have, again, a multiplicative error term. Okay. So this is all going to produce, whether it's you take a model with additive errors or multiplicative errors, as long as the parameters are the same, these models would generate the same point forecasts, but the prediction intervals or the uncertainty associated with point forecasts is going to be different. Now, when we take this idea to R, we are going to be using the ETS. Again, make sure that you have this in caps and this is not in a lowercase. So ETS is the function that you're going to be using on your observed time series Y. This could be anything, right? Here we're just calling it Y. And then you have your the expression of your model. So if you were looking at estimating a simple exponential smoothing model, this is going to be using the ETS function. You're going to regress your observed time series on the different components here. Okay. Now, the only thing we care about is the error component for this type of a model, because we don't really have trend or seasonal component, so that's not there here, but the error term itself is additive. If you ever wanted to control manually what the level of alpha is, although I don't foresee that happening because R can actually automatically produce models optimizing the level, initial level, and the smoothing parameter alpha. Even if you needed to change that alpha, you can do so by just changing something in the trend function here. Okay, so that can be chosen by either replacing the default option by saying alpha equals some value that you can specify, or you can present a range of a specified range for alpha, okay, by calling this and augmenting your arguments in this fashion. Now, going back to the Algerian economy, that is a subset of the global economy dataset that's available in the third edition of your text. We start with looking at Algerian exports. Okay, you can try any other country at home, but here what we're doing is, in the first step, we are trying to filter out all the data for the country Algeria. Okay, so we're going to call this Algeria underscore economy. This is coming from the global underscore economy data set, and we are filtering using country equals Algeria. Okay. In the next step, we are going to fit a model to the data on the Algerian economy. It's always a good idea, once you have Algeria underscore economy just at home, try to use the function head Algeria underscore economy just to look at what the data looks like for you. Okay, but there is going to be data on the Algerian economy. Okay, and so we're going to be focusing on the exports. Okay, of course you can look at many other different facets of the Algerian economy, but in this example, we're focusing on exports. So the fit is going to be equal to this type of a model, which is coming from the Algerian data set. So here I'm writing model. Okay, whether you have one model in here or you have two models or many other models, you're going to use the model function, which is very powerful, and we are going to call this ANN. Okay, now this type of notation tells you exactly that your error term is going to be additive and there's no trend and no seasonal components. Okay, so it's easier to call ANN as the model that you're estimating, but feel free to call it whatever you think is helps you remember it. Okay, so that is going to be equal to ETS. Now you can change this. This is a function that you must use. And within ETS, you're going to replace this by the time series of interest. So if in the previous slide I showed you y is going to be exports here, because that is what we are trying to work with. And exports is going to be regressed on this sort of a model, which is written here. So the error component is additive, the trend component is not there, again, the seasonal component isn't there. Okay, and then you can use report fit to see what you get here. So once you look at the output, this is saying that you have estimated an ETS model with additive errors, no trend and no seasonal components. And the smoothing parameters, here there is just one smoothing parameter because we are just looking at the level, and that is alpha equals 0.84. Now a large value of alpha, right? If alpha is 0, then we're not updating the time series at all. If alpha is large, then this is indicating that there is a large adjustment in the estimated level in each period. Okay, so the level is LT, and that is going to be updated each period. If you look at the time series of the Algerian exports as a percentage of GDP, this kind of looks like it's going all over the place. So you would expect the series to be, once you have estimated the model, you would expect that you would actually get a higher value of alpha because the level has to update for a model to be good. Okay, and then it has estimated the initial states. Okay. So this is saying that the initial state is 39.54% of exports as a percent of GDP is 39.54 for the Algerian economy. And then there are some other diagnostic statistics that are given along with this. Okay, now sometimes you might want to look at different things for from the output that is produced. Here you can look at the fitted model one more time, and you can look at its different components. So if you want to look at, what's the level, what's the remainder, what's the fitted value, you can take a look at all of those, and all you have to do is use this left join command. You may or may not want to do this, but this is just something you can do if you wanted to really get in deeper into what everything is everything looks like for the Algerian economy after we fit in the model. So you're going to say left underscore join, call the fitted columns from the fit variable that we had defined, and we're going to do this by country, model, and year. So country, model, and year are going to be augmented on the left side. Okay, so the more important thing is we want to get to the forecast. So let's say we were predicting 5 years ahead. We're gonna use the fit model that we had estimated before, and we're gonna use the pipe function on this and say forecast H periods ahead. Okay, so H is 5, which is 5 years ahead, and then we're gonna auto plot the data. So auto plot means we're just looking at this time series, okay, and plotting it with the forecasts. And you can see here that the simple exponential smoothing models has generated a flat forecast, okay. So this is important to remember. Anytime you have a simple exponential smoothing method or model, it is going to generate a flat forecast function. So all of the forecasts in the future are going to take the same value as the value of the last level component. So if you notice, this last value right here is sort of extended into the future, okay. But notice that there's a lot of uncertainty associated with these types of forecasts. So yes, we expected that because we're looking at a very simple model, but that's where we have to start.